Stream Deck. I'm back. It'll be interesting to see how we'll have to clip this together somehow when exporting to YouTube. God damn it. All right. So, let's see. What were we doing? I was pressing this to get to. I have a button on my Stream Deck that kills everything, and it's important to kill everything because if I shut everything down cleanly, preferences are saved, and then OBS gets broken, and it's just a nightmare. All right. Anyways, basically streaming is hard. So let's look at chals. Heap chals are still not live. They are live. All right, so you have 15 levels of Heap challenges. Each Heap challenge has a teaching and a testing instance, as usual. And let's dive in. So let's see if anyone's already solved. Still no solves. Let's see, there's got to be a first blood soon. All right. So what am I going to do for the rest of this class? I will continue sipping my tea. We'll also... All right, let's see. Ooh, one solve by H. Cree. Good job. Baby Heap. 3 solves. Nice. So, let me show you a couple of things in the Heap. First, I'm going to start up this practice chal. Let's yeah, for people wondering how H. Cree solved it so fast, maybe it is it could be, I mean, I don't know what they're doing exactly, but a lot of these challenges are similar to last year, because it's just the material, right? We've tweaked them, but oftentimes the solutions transfer quite well. Not a big deal, except for, early on with the scoreboard rankings, but that's okay. H. Cree will have to work plenty hard to stay on top, and they've demonstrated their ability to do that. Holy crap, 8 solves. Great job. All right. So, the level 1. These Heap challenges provide you with a Heap playground. What does this mean? Normally, of course, in your in a, god damn it, I reconfigured my pwn.college environment and now everything is fucked. Anyways, all right. Normally speaking, you have your program that does allocations, freeze, and so on with various pointers. And as we discussed in the lectures, malloc, free, and this family of functions of Heap allocation functions, calloc, realloc, etc., they do a bunch of operations and a bunch of metadata in memory to provide you with space that is safe to write to and read from. All right. So, all right. Actually, I am very impressed at how many solves H. Cree was able to do in 2 minutes. Even if they've done this ahead of time. That's insanely fast, just to apply the solutions. All right. Anyways, let's get back to business. All right. So the baby heap challenges provide you an allocation playground where you can use program functionality to trigger allocations directly for the most part. Now, is this a realistic hacking scenario of using heap vulnerabilities? No. Usually in a real program, you have to trigger program functionality that then uses the heap in some way. Here we give you direct access to the heap. Why? Because that's how the baby modules work. The baby modules allow you to explore directly the concepts that you're dealing with. That is why... now my mind's drawing blank. Baby shell would just automatically jump to your shellcode and so on. Then that gets put together in toddler 1 and 2. So the goal of baby heap is for you to learn the heap, to learn how it can be corrupted, etc., etc. Toward the later levels, we do some truly clever stuff. But for the last, to put it all together and actually use heap insanity in the course of real exploitation, that's where toddler 2 will come in. All right. So, all right. I'm sorry. I'm refreshing the scoreboard. We're starting to have a heated competition. Great job, H. Creary. That was so fast. Even just putting in the flags. All right. Anyways, that's a true hacker spirit. So, question in Twitch: are we calling it heap massaging or heap feng shui? I usually call it heap massaging, and that is the art of arranging the heap in a perfect way by interacting with the program so that your exploit can properly land. All right. So you launch the challenge, and the challenge allows you to allocate free and so on. Wait, Connor, where's the debug? I want to show off the new feature. Is it in a later level? Ah, my Tcache is empty. Dude, we should still... it's auto. Okay. So, Connor and I added some functionality that as you use... so I want to call malloc 16, right? All right, so I allocated a 16 byte buffer, and it's right here, and I can free allocation 0. Sorry. I can free the allocation, and here we have a debug output that will give you the state of the Tcache and the specific bins and the entries in those bins between every interaction you have with the program. So you can truly track that. So I malloced something. It returned this value. When I freed it, the value went into the Tcache. Here it is, that entry in the Tcache. Its previous size is 0. Yeah, because it has no previous. It's the first chunk. Its size is hex 20 with the prevent use flag set to on, which it always is. Well, that's not true either. Why is the prevent use flag set to on? To true. If this is 0. Previous size. Because this is the overlap with the previous chunk. Okay, yeah, so the previous size, the previous chunk is in use, and then the next pointer is null. There's only one entry in the Tcache, and the Tcache key, which is the location of this Tcache struct metadata, is that, right? And you can see here the how values change as you override them and so forth later in the program, later in the module as you start messing around with malloc stuff. All right. What is inversed? Oh, why is it inversed? Let's prevent use. Okay, let's see what Connor linked in Twitch. Size of chunks, size of next chunks. That's okay, yeah. Size of previous chunk, size of chunk in bytes. Okay, the pre-flag stored in the unused low order bit. It's an in-use flag for the previous chunk. If that bit is clear, yeah. So if it's in use, the first chunk allocated always has this bit set. Awesome. Okay. Awesome. Yeah, that was correct. As you can tell, even I forget some of this stuff. Cool. Okay. So we allocated a buffer, we freed it, and then our Tcache was warmed up, initialized, and has data in it. And the teaching output now gives you the state of the Tcache. All right, how did I even know to do all of this? To do malloc, blah, blah, blah. Well, of course, I wrote this, but we have to reverse engineer the program. So let me copy the challenge. All right, and then we can open this in IDA. All right, here we go. This is the main function of the baby heap level 1. We decompile it. It looks pretty bad, but not too horrible. Usually when you see this nested loop of while ones, let me increase the font a little bit. Is that better? I feel like that's still going to be tough to look at. All right. Usually when you see this nested set of while loops, it's a switch statement that's been improperly decompiled. And then all of these individual parts is the different cases. So what seems to happen here? Okay, so we do this Tcache debug print. We print this string, whatever was here. Oops. No, how did I mess that up? Oh, it's a bunch of null bytes? Why? Okay. Let's avoid that. We print the menu, blah, blah, blah. All right. So, and then we scanf a word up to 127 letters, right? If that word is malloc, so malloc followed by a space or a new line, we ask for the size. If that size, we read the size as a string, we convert it to a number, and then we say what we're about to do, we do it, and then we say what the result was. All right, and it's similar for free. We free the... okay, so yeah, so we have this variable called pointer, which is a variable on the stack here. When you do malloc, it'll store that the return value to that pointer. When you do free, it'll free that pointer. When you do puts, it'll puts that pointer. When you do read flag, it'll malloc something of size, and this size is probably different for everyone. Size 753, and it will read the flag into it, and that's it. So what do we do? Well, let me run you through this to show how the this challenge works in terms of showing you how to abuse the T-cache to get what you want, or the cache in general to get what you want. So let's run it. Say okay. Remember that number. When we do read flag, a buffer of size 753 will be allocated, and the flag will be read into it. But what if we create a buffer of, we do malloc 753 bytes. So now we have an allocation. T-cache is still empty. So if we do read flag, the flag buffer does a malloc of 753 bytes. That gets us a different value. So our allocation that we created is at this address, ending in 82C0. The flag buffer ends at 85C0. And there's the flag in there, but it's inaccessible to us. We can't really get it out if we do our puts. There's nothing in our allocation, right? But what if we free our buffer? It goes on the T-cache for T-cache bin number 46, which is for sizes 745 to 760. And now if we do read flag, the program allocates 753 bytes, which goes straight to the T-cache and gets, because that bin isn't empty, gets the first entry in that bin, and that's our flag buffer that's returned. Now, if we do a puts, which, let's go see what it will do. A puts will, right here, so if circom puts return 0, it won't break out of this block into this block, so it'll execute this. Again, this is a very, very badly decompiled switch statement because of just how it looks like from a control flow perspective, because it's wrapped in a while loop. Switch statements and while loops are actually difficult to decompile in the general case. But if you puts, anyways, if we do puts, it'll just call puts on our pointer. And so we just had the pointer allocated. We do puts, and we get my local flag stored on my computer. Cool, huh? So we abused the T-cache. And why were we able to do this? We were able to control this allocation. This is T-cache functioning as intended. We freed a previous allocation, and we were able to induce the program to allocate that old chunk back out of T-cache into service. That's supposed to happen. What's not supposed to happen, and what was the bug in this case, is this puts. Puts used the flag buffer, or puts used the buffer, this pointer, without checking if we were supposed to, if we had freed it or not. So what's happening is we're using a dangling previously freed pointer, and as a result, we're able to read data from that in some sense the wrong security context. The program thinks data at this pointer is just for the user, whatever, freely available to read. But in actuality, because this pointer wasn't invalidated after the chunk it was pointing to was freed, we're able to use it to leak out the flag, and which is a common kind of situation with heap bugs in general. All right, So Ethan said that they're seeing puts output the free table. Oh, I see what you're saying. Yes, if we do this free, right? So now we freed the flag buffer again, but that's fine. We do a puts. This is the data that puts output, and then this is the debug. Puts isn't responsible for this being printed. This is the teaching code responsible. So if you are seeing this, it's you're screwing up the actual situation. So for example, can I induce it in this one? No. In later ones, you can actually play around with overwriting this metadata and seeing it change and seeing what comes out of this data print change as well. But this, again, this is not puts printing it out. And if we spin up, I guess an easy way to show this to you is to spin up level, the teaching level, and it doesn't have that. Here's the teaching level. Again, malloc, I don't know, read flag. See, no output, none of it. Free puts. It's just our data here. It's empty data. And why is it empty data? Well, it's empty data because when this is where your allocations point to. And when you free, unless you have multiple allocations, multiple chunks in the T cache, the next pointer is nulled out for the last chunk in the T cache. That's why you're getting blank data. All right. Let's see. Connor said level 4 is the first with a scanf. I think it's a good idea. Let's take a quick look at level 4 to show you what happens when you start overriding things. All right, so now level 4 is created or is launched. All right, so here's level 4. Okay, so this challenge allows you to manage one operation, but it also gives us a scanf functionality. What the hell does that do? Well, let me open it up in IDA and we'll see. Again, this horrible decompilation of a switch statement. Why is it taking so long? There we go. All right. So we have malloc. As usual, it's the same sort of thing. It just has a pointer. So we get one allocation. We have free that just frees the pointer blindly. We have a puts, which puts the data. We have a read flag. Now, what does this read flag do? This read flag will 2 times do a malloc of hex 105 for my specific instance, 261. So it'll do 261 mallocs, and then it'll read the flag in. Sorry, it'll do 2 mallocs or 261 bytes, and then it'll read the flag in. Why is this a problem for us? It's a problem for us because if I do the same attack, malloc 261, free, the T cache is all warmed up. Now if I do read flag, it does a malloc once. It gets what I put in the T cache out. It does the malloc again. And I'm screwed. The new data is not something that I control. If I do a puts, there's blank data there. Okay, so this challenge, I'm not going to solve it for you because that's up to you, but this challenge allows you to do this scanf. What does the scanf do? Scanf allows you to read into your allocation. So it figures out how much it should let you read, and then it gives you that scanf of that much data into your buffer, right? So if you do, I have this, let's do a malloc 261. Okay, I can do a scanf, do hello. All right, I've read that into the buffer. I do a puts. Here's my data, right? But the bug in this one is that neither free nor scanf make sure that the buffer is actually allocated. So again, we can do a use after free. I can free the buffer. Here's the Tcache. And I can do a scanf. And I can say A, B, 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 as we saw in the video. Boom. And I am actually overwriting Tcache metadata. So this next pointer is now overwritten. And the key is overwritten. Because the key is overwritten, the next time I do a malloc for this much data, what was it, 261, right? It can actually be anything in this range. So that whatever, 250. It happily returns it. Is it just on a free? Okay, here's my key. It's just on a free, isn't it? Let's see in the malloc source code real quick. Okay, actually, this is a very good learning opportunity. What the hell? Hold on. The browser lost connection to the browser. There we go. Okay. OBS is very annoying. All right. If we look at... nice. People are racing up. Wow, look at this bundle of... huddle of ASU people at the top. That's crazy. All right. If you're in doubt, like I just was, where I expected malloc to tell me to go screw off because I corrupted the key, but it didn't. Because the heap is tricky. It's easy to mix stuff up. Don't forget the malloc source code. You can always read it. Now, reading the master branch is a little tricky because malloc changes a lot, but this malloc seems to be frozen in 2018, which is good enough for us. That's roughly the malloc that we're using. And we can search for Tcache key. Oh. Tcache entry. Yeah, okay. So here's Tcache entry. No. Connor, you linked us to a too old version of malloc. One sec, Connor's getting the right version. Actually, in the meantime, I'll show you what I do for malloc. So, if you're on Ubuntu, you could do apt get source libc. Well, I guess that is, yeah. glibc. It grabs libc. And Ubuntu uses glibc 2-31. You can also click the link that Connor uploaded on Twitch, some other link. But here we have the glibc 2.3.31 source code. And in there somewhere is malloc.c. And here is our malloc.c. All right, this source code is not too bad. It's 5,610 lines of C code that ideally you should understand inside and out. But of course, no one is that insane. So you can search it for specific implementation details. For example, if we search for Tcache, we find this Tcache entry struct, and we see that there is a next pointer and the key that we saw the output of. If we search for other uses of the key is saved when something is put into a Tcache, and when something is gotten out of Tcache, it's nulled out. and it is only checked when, what is this function? When we freeze something to add it to the Tcache. Okay. That's right, sorry. It's hard to keep all these malloc implementations and versions straight. The key is just there to prevent double freeze, as we discuss in the lectures as well. But obviously, I should have kept that more straight. The key is there so that we don't free something twice. Let me show you what happens. When we free something, if Tcache is used, which it is, it checks if the key of the allocation we're freeing is equal to the address of the Tcache per thread struct. If it is, it goes through that entire bin of those size chunks and makes sure that that chunk isn't already in there. And if it is, it errors out. So let me show you what that looks like. So we freed one thing. If we try to free it again, boom. Double free detected in Tcache 2. The double free is because it saw that the key of the chunk I was freeing, rather the data I was freeing, the allocation I was freeing had 8 bytes into it, a value that matched the Tcache key, and then it went through and found it in there as well. So for example, I can now do a malloc. Let's just do 16, a free. Here's my Tcache. If I do a free again, I'll trigger the double free. But if I do a scanf and override it with something else, and I do a free, it'll happily do it. Because when I did the free, the key was not pointing to the Tcache bin 0. Connor, isn't this... Connor, what's the difference between this key output and this key output? And why did it end up being 414141 here as well? Yeah, this might be bugged, guys. We might have to fix that, but that's okay. This is correct. Yeah, Connor, this should just be the address of the Tcache struct that we're printing out anyways, right? Cool. Okay. So now, of course, if I do a free again, it detects the double free, because when it freed and added that same chunk into the Tcache bin, it fixed up the key, because that's what it does when something is freed. But we saw that because we read the source code, and as we saw, this source code is really not that hard to approach. If you want to look at where malloc is implemented, nope. What the fuck? Yes, internal malloc. The malloc logic is actually not so bad, right? It's just, I mean, okay, this isn't that little code. But once you go through it once or twice, not that you'll need to for this assignment necessarily, it's only 600 lines of code for the malloc function. Free is very simple if you truly want to understand it. It is only 275 lines of code. Not too bad. And you can understand this logic, and then you'll truly understand what's going on. Or you can interact with these at a high level and kind of intuit what is going on that level. All right, so let's check in with our erasers. Awesome. HCRE remain. Oh, Genesis is catching up. Genesis, did you also do this in the past? HCRE and Genesis and Dirac Delta and trees are locked in a dead heat. Yeah, so it's super approachable. You can see, right? Even Genesis managed to solve 7 super fast. No, I'm just kidding. It's just they're super fast. And HCRE, you gotta stay ahead. Come on, what's going on here? What level did HCRE reach? They skipped level 4 and went to level 5. Interesting. I wonder if there's some unintended solve for level 5. I would imagine that level 4 would be... If you... Yeah, interesting. Connor, why does level 4 trip people up, but not level 5? Does level 5 allow you to make multiple allocations? Like with different indexes? Let's see. Yes. Okay, that's why. This challenge allows you to manage up to 16 allocations. Yeah, that makes a lot of sense. Cool. All right. So that is the heap. We got 5 minutes left in class. One thing that I will mention that a little bit of, let's say... So this class follows the latest long-term support release of Ubuntu, basically. The heap changes on a daily or a weekly basis, right? Some of these... is mayonnaise an instrument? What? All right. Some of the changes in the heap are because security researchers find issues. Some changes in the heap, as I discussed in the lectures, are because people want the heap to go faster. And then these changes go back and forth in shifting security versus performance of these implementations. So, what is the current situation, right? As I mentioned in the lectures, on the latest Ubuntu 20.04 at least, the current situation is basically the Wild West. Tcache is almost completely unprotected. The only real thing is the Tcache key. Even that was a bit of a, change that took a while. That Tcache key didn't used to exist. You used to be able to just freely double free to your heart's content. Now at least you have to be a little careful. But what does exist now is the shift back to secure world. So the next iteration of this class will be run on Ubuntu 22.04 next fall. Ubuntu 22.04 will run with a heap feature called SafeLink. Let me show you this. Safe linking. This is just the first blog post that came up when I searched for safe linking. Basically, the general idea now is that the modern implementation of Tcache will protect the metadata. Also, fastbins, anything that just has the simple forward linked list, will protect the metadata with a random, by XORing it with a random number that's known to libc, but not known to the attacker. So again, very similar in style to ASLR, kind of, but a canary for sure, right? You have a random piece of data that you must know to successfully mess with these structures. It's going to fundamentally change much of this module. Of course, attacks on the heap are still very much possible, but they're going to be a lot less trivial. And they're going to be a lot less trivial in a similar way to how attacks, Stack Overflows are much less trivial with a canary present. Where in order to do many of these things, or how, pointer overrides are less trivial with ASLR, you'll probably still be able to do relative games by overriding just the last byte or something, but you'll likely need to have a leak component to most heap exploits. We haven't figured out the material yet for next year, but it'll be very interesting to see what it is. Cool. Any last minute questions before we call it a day? There's a question on Twitch. Double free is only useful to populate entries in the T-cache. Yeah, or other cache, or other bins in libc. A double free allows you to basically induce overlaps later when things are allocated. A double free is usually used to induce a use after free. Kind of to induce basically the use of the same allocation from two different contexts. All right. The other thing was the command in GDB to go back an instruction. If you have recording on, it's RSI. Cool. Okay. What's one more thing I want to mention? Oh yeah. Tomorrow, I think as long as Connor is available for office hours, I think Connor, it would be good to go over like Jeff and Pwn debug, whichever one you want, for their heap debugging functionality. And then again, very, very much beg you not to sleep on these challenges. These rock stars have made it through quite a lot in a very short time, but this is hard material for a lot of people. All right, so please give yourself the best chance at success. Also, let's just double check. Let's look at the Asu Academic Calendar. I believe the withdraw deadline for those who need to withdraw is tomorrow. So please, I'll send out the iGrade policy on Canvas, but please keep that in mind. I hope everyone, of course, stays in and does great, but everyone has different situations. All right. Let's call it a day. I'll see you on Thursday for more Heap. And go do the challenges. Don't wait. Start now. Please do the first couple. It's super easy. It's a little Heap playground. Or not super easy, but it's super approachable. So, good luck.